Yes. We will swap machines. And the title of the second paper is Replication Based Self-Learning of Mobile Agents Exploring Complex Networks. And it will be presented here by Arles Rodriguez.
Okay, thank you very much for being here. I am Arles Rodriguez from Fundación Universitaria Conrad Lorenz. And I'm working in cooperation with Jonathan Gomez from Universidad Nacional de Colombia and Adam, who is here, from Telecom Paritech. And I'm working on this work entitled Replications-Based Self-Healing of Mobile Agent Exploring Complex Networks. And the motivation of this work is to achieve data collection and synchronization in distributed environments by using the power of multi-agent systems. Multi-agent approaches offer scalability, offer robustness, and offer also flexible solutions for doing this kind of task in different and large distributed environments like sensor and ad hoc networks or distributed clouds, or even for distributed caching and different environments. As a previous work, a first approximation was to design this simulator. Our agents are simulated, and the idea here is to use them for collect or for synchronizing data. So as you can see in the image, there are agents in a determined environment. In this case, it's a topology that corresponds to a network. So the agents move in the network and they collect or synchronize data that is distributed in each location in this network. And the idea is that they exchange data with the nodes and other agents that are in the same location. And what we introduce here is the concept of fail. When they move from one location to another, they can fail with a certain probability of failure. As a network, we define different topologies. As you can see in the image, the yellow points are the current location of the agents. In blue, the explore part of the map or the topology. And in red, the locations that hasn't been explored previously. So this is more or less how the simulation looks like. So you can see how the agents are moving and turning the graph from red to blue in the way they explore and collect the data. The agents can fail, they are moving from one location to another. It defines failures in this point when they are moving initially. So with certain probability, when they try to move from one location to another, they can fail. As a previous work, we're starting with model different environments. In this case, and for this paper, we work with different configurations of networks that corresponds with topologies of distributed systems like the small world or the community networks or scale-free networks. Each kind of networks with different characteristics, and we see how faster algorithms complete the task even with higher probabilities in the case of data collection or synchronizing data. Each one of these networks has different particularities. In this case, the network is rewired in a probabilistic way. In this case, we have central hubs of information, like defining some kind of topologies of typical clouds of distributed systems. And in the case of the scale-free, you can see also different hubs or different weak connections between the nodes. So there are different environments, or classical environments like this lattice that you can see here, that corresponds to simple grid. So in this work, the goal is to support higher probabilities, because just by putting the agents to move, we obtain data synchronization of data with a probability lesser than this one, 0.01. So we want to support higher probabilities, modeling failures in that way. The approach here was to detect agent failures. The most common way is to using timeouts, so we use that. And we use the timeouts for creating new agent replicas from these agents that move. And here, so the problems we address are how to adapt the timeouts to changing communications delays, because in real environments, communications have, each link has different speeds, so they have different delays, and we need to adapt these timeouts in the movement of the agents to detect the failures and to create new replicas. And in second problem is how to avoid agent over replication. Let me duplicate the desktop. If we model a higher failure probability, as you can see here, there are some agents that try to explore. That's too fast. They move, they explore, and they fail with this higher failure probability without replication that is expected. So we explore and collect data just for a few nodes, the nodes in blue, so the nodes in red are remaining. They don't explore that. If we model a timeout and assume that the agent's movements has no delay, is the same failure probability, we can see here that new replicas are recreated in the way the agents fail. So they achieve to explore the topology and do the tasks they were designed. What's the problem here? If in this case the timeout is bigger than the time of movement of the agents, than the delay. In the case when we define a delay in communications, for example, like this, they start the same agents, they start movement. If the timeout is smaller than the time the agents take, they move, we have problems here because the system will create a lot of replicas. In traditional systems, the timeout is static. So what we want to do here is how to adapt these timeouts, and that's the main objective of this work. As a solution, we propose messages as part of the solution. In a way, each node is responsible for a set of agents that departs from a node and arrives to another. In this vector, the follow agents that stores references of the IDs of the agents. When an agent departs from a node, they send a message to the current location. And when the agent sends this message, we add the agent to this vector. When agents arrive to a destination, we send the free responsibility message to the previous node. So we delete from this vector. The timeouts, there is some kind of learning of the timeouts in a way that we store the difference between these two messages from a determined location. So this is how we compute for a destination of an agent. So in the topology, we are having some approximation for each network that is different for each connection, and is the differences between the time of these two messages. This is basically what we are doing here. And we update the timeout based on this vector. We We create a new replica if the estimated timeout expires. So based on this expected message vector, we compute the median. And by assuming some normal distribution initially for this work, these 3 standard deviation outside the data, from this point we create a new replica of the agent. Yeah, we just assume this normal distribution right now. So after that we create new replicas. We can have a false positives. So in case of false positive, what we do is just how to discover a false positive in this case. The agents are moving and sending message. So if we create a new replica and after receive a message that the agents arrive to the location, we delete the next replica that passed through this node. So in this way we are controlling the over-replication. From the previous work, we select the challenging networks. There are these 4. The small work, this configuration, and the community network, which is 1, the scale-free with a low degree of connection for some nodes using and central hubs and the hub and spoke. The experimental settings and experiments aim to determine if we adapt the timeout, and determine is if by proposing this approach we deal with the agent's failure and avoid the over-replication of the agents, and also to assess the system performance in terms of time and overheads in terms of memory. I'm going to present the data in terms of rounds for some configurations because there are a lot of results. We show here the relevant and the beautiful results, so the rest are in the paper. When we think in terms of success rates, in the way I increase this failure probability, then the percentage of successful reduce within the failure probability. So without failures, it's expected that we synchronize data in all the simulations, in all the experiments. We execute each experiment 50 times. And in the way we increase the probability without replication, after this point we don't obtain any experiments successful because the agents doesn't explore the agents don't explore the network. With replications, all the experiments were successful, even with this high failure probability of 0.5. So in all cases, if we apply this kind of replication, the agent synchronizes and collects data from the network. If we define that the agents move instantaneously from one node to another, they move faster, and define in this case a short delay, because the agents move fast from one node to the other. We run the experiments 30 times. It's 1 from 30. Each point in this graph corresponds to the minimum, the median, and the maximum number of agents for a simulation. And this graph shows how the number of agents versus the simulations. So we can see here how this proposal is adapting the timeout. In this case, they move fast. So if we start with a static initial timeout of 10 rounds, and within the time, initially you can see how in some point of the time we have 0 agents because the timeout is too big. So there are moments in that we don't have agents exploring. Within the time, what we obtain is that the median approximates the maximum number of agents. We also always start with these 10 agents. So after some simulations, the timeout is adapting by using these rules we propose here, even with this high failure probability. These results are for a small world network. The other scenario is when we see the agents are slower, the communications are slower, so the agents will take more time to move from one node to the other. So if the timeout initially is static and is smaller than this time, in the beginning we will have a lot of replicas, like 175, something like that. Within the time, what we see here by applying the same rules, the over-replication is controlled and the timeout is adapted. You can see here how the maximum number of agents reduces within the time in the way we execute the same simulation and store the vector that allows us to compute the difference between times and adapting the timeout for different failure probabilities. Because there is nothing that is perfect. The impact here is in terms of time, because the agents are exploring, the experiments are successful, we adapt the timeout, but after some failure probability, you see here, the time taken for the agents to complete the synchronization task increases. This is the timing rounds, as you see here, and this is the failure probability. So a higher failure probability impacts the timing rounds taken for the agents to complete the synchronization task. Even as conclusions, this proposed approach uses replications to deal with the agents' failures. We are adapting the timeout to communications change, because we learn from each link how more or less an approximation of the timeout, and we delete replicas to avoid over-replication. But for the case with no delay, we obtain a maximum number of 4 replicas for all the 30 experiments for a topology, so we have a small number of false positives. The impacts on the performance are basically in terms of failure probability, because it impacts time, and in terms of network topology, because we obtain the best results with the small world and the community network, and the slowest network that needs more time to adapt the timeout is scale-free with a low degree of connection. That's the network I showed you before in the video. As current work and an application of this replication we are proposing here in PAAMS is to try to recover the network topology. So this is a work in progress. So you see here we have the agents that explore and collect. In this case they collect the network topology information, and you see here how nodes disappear and how they recreate the nodes. If a node fails, the agents on these nodes fail. So we pretend to use this kind of replications to maintain the network topology, integrity of the network topology. This is the blue line, from 0 to 100%. And you see here how the agents reduces in the way they fail. We are working on that thing now. As additionally, we also propose here for PAAMS a demo. We wait for you in the coffee break late. We are presenting this teaser of the different simulations. We now are working with complex networks, but before we start with mobile agents that explore a bidimensional space, as you can see here. There are agents that use different movement strategies for explore a determined network. They collect information. We can see here how they collect that. We inspire the topologies in the complex network topic just to manage this kind of exploration and study different network topologies and establish metrics in terms of resources consumption and in terms of replication and self-healing. And this is what we are our work. If you have any questions or comments, thank you.
Thank you, very good. Some questions from the floor? Yes, please. Just a brief presentation, please, of yourself.
Okay. My name is Hared Yeditsian. I'm a postdoc at Replication University in Israel. And I would like to ask about the communication model between the agents, or how they share information. The agents.
Okay, in this case, we assume, for example, that each node is a server or virtual machine instance. So the agents in this node exchange information through the node. So imagine the agent like a process that exchanges information to another process in a current instance or server. So by staying in the same space, this is the node, they exchange information. In this case, that is a simulation, we use a typical serialization of Java that we use to communicate the process.
So, for example, an agent visited a node and
They detect
detected it.
they detect another agents in the same node and they exchange. Or the agent visits the node, left information in this node like an ant that left pheromone, and another agent reads this information that is in this node.
So only when another agent reaches that node would he know that it has already been found by another agent? Or would he know beforehand?
Yes, but they can also read information that is in this node. In the case of data synchronization, by example, we can collect also information from the node.
So if I can just quickly clarify, I think you're right. So the agents exchange information when they're on the same node.
Yes. So they wouldn't know before, they would have to visit that node to know that it was already found by another agent?
No, if you want to know that, then there are some algorithms that leave pheromones on the trail, and then if you don't want to visit a node that already has been visited, then you avoid it by smelling the pheromone trace to it. But that is more the exploration technique. But then in terms of agents actually exchanging the information that they have, that only happens if they meet on the node. I don't know if that answers. Yeah? Okay. That's what you've been saying, but...
Yeah, that's good.
Yes, please.
My name is Anna Paula. I'm from the University of Porto, Faculty of Engineering. And I like to ask you if I understand well, when a node arrives to the destination, it tells the first one that he arrives. Okay?
When the agents are moving. And
Yes, when one agent arrives to a destination, it tells the other node
the previous
he arrives.
location that
Yes.
they sent.
So, it's not a lot of information. Can't you decrease that information by, for instance, some prediction of a failure will happen or not?
Yes, we control that because this is a trick here, and we have a small amount of agents respect to the size of the network. So in this case, the network is size 100 nodes, more or less, and we are using just 10 agents for exploring the whole network. We are evaluating now.
But if each time the node,
Yes,
the agent arrives,
exactly.
it
But
must tell something to it.
exactly, they send the message to the previous
It's a
node.
lot of messages.
But we are in this moment estimating if there are less messages compared to broadcasts. We think that yes, because we have a small amount of agents. So what, as Ada said, with a good exploration technique, we synchronize that data faster, and we need less messages for achieving the
I was
same.
wondering if you have some kind of learning or prediction or what else, if you could minimize this communication.
If we could learn the probability of agent failure, like we're imposing it here, if we could learn that, then we can create agents with that probability and it will be fixed. That would be a solution, if that's possible.
Yes.
Yeah. And if that weren't dependent then on the part of the network or things,
Some parts
sure.
maybe
Yes.
more failure.
Yes, I'm sure. Yeah, thank you.
Thank you.
More contributions, comments, questions? Just a curiosity from my part. Have you approached the problem of the relation between the number of agents and the dimension of the network, for instance?
Yes. In the first experiments, we see that a higher number of agents means a higher exploration of the network. So we play here with different variables, the failure probability, the number of agents, and the topology of the network.
But is it linear? When I have a concrete network, how can I estimate what is the optimal number of agents? It is not so clear.
Yes, in this moment we talk about profiling because we are looking for a way to achieve the task. So and we are not thinking about optimize. We compare and profile and say this in previous work, this exploration technique is faster and synchronized data faster. But we are not looking right now for the optimal choice. We just profile and compare the different techniques.
Okay, maybe we can learn then from those experiments and come up with some rules and so on.
Exactly. By now we find configurations that work fine and try to extract the metrics. And
thank you. No more questions? So thank you very much.
thank you so much. Thank you.
And our next paper is titled Managing Disruptions with a Multi-Agent System for Airline Operations Control. It will be presented by Antonio Castro. We are swapping machines again because we want to make sure that this is the ideal machine